major, yeah.
Were those? Go back.
Yeah.
Were those two consistent with each other, the intermediate and the deep?
Yeah, so it's a little strange how this turned out to be slightly different. This is 68% confidence intervals, I think, so in the end they were consistent. But I think it also does tell us that there's improvements that we can probably make in the color magnitude diagram to star formation reconstructions also. These do include stellar library errors as well. But obviously that's not going to be the major source of uncertainty there. So we can start to then address some of these major questions in galaxy formation. So what are the properties of first galaxies? How does reionization affect galaxy formation? At what halo masses do we expect the occupation fraction to fall below 1? So where do we actually start to expect to see dark matter halos? How does this all depend on the assumed dark matter physics? And are some of the small scale issues in galaxy formation that we'll probably hear more about this afternoon, are they issues for galaxy formation or for cosmology or dark matter or some combination of the two? And just to give a little advertisement, Alex Fitz will talk about this a bit in the next talk. This is what he looks like from previous life as a J.Crew catalog model, I believe. Right. Okay. So one potential worry in all of this, of course, is that the local group is sort of by definition a special environment. Now we have the cosmological principle, right? We're not supposed to live at a special place or time or whatever. But the local group that we can actually probe is relatively small today. It's something like a couple of megaparsecs. We know the scale of nonlinearity is maybe 10 megaparsecs. So in a sense, we're in a nonlinear regime here. So we're not studying sort of nice linear physics. And so maybe the small size of the local group means a special environment. To put that in a bit of context, here is the Austria Simulation. Okay, something like 100 co-moving megaparsecs on a side here. The density distribution is shown of the dark matter. And you can see the local group right here is this little square. So it's some small region in this large cosmic web at the present day. And if you move that square around, you're going to find very different densities depending on where you put that square on the screen. Right? If you go back in time, of course, what happens is the dark matter density becomes smoother and smoother. So this is running the movie of structure formation backwards in time. And that means that we get closer and closer to the mean density. But another thing happens as well. If you look at the local group, that's now a somewhat collapsed object. That means at earlier times, in a co-moving sense, it was a much larger object. Okay, so this square for the local group actually expands as you go back in time. So two things are happening. The universe is getting closer and closer to the mean density, and the square that the local group is probing is actually getting larger and larger as we go backwards in time. So actually, at redshift 7, so in the reionization era, the local group came from matter within a sphere of something like 5 megaparsecs co-moving radius. What that means is if we look at this 2 megaparsec local group today and put it in context to earlier times, it's actually collapsing from a much larger region, right, that's probing a much more representative part of the universe. Another way to think about this is let's put it in context with the size of Hubble's field of view. Okay, this is, of course, one of the most famous images in astronomy here, the Hubble Ultra Deep Field. And if we put that onto this kind of plot I've been showing here, that's what it would look like at redshift 3. It's actually smaller than the size of the progenitors of the local group on the sky. Even at redshift 7, it's something like comparable to the size of the progenitors of the local group. So for pretty much the entire history of the universe, the progenitors of the local group cover an area on the sky that's larger than what the Hubble Ultra Deep Field covers. And so I think we can think about the local group in the same context of this as something like, well, the Ultra Deep Field is showing a series of slices, so there are galaxies at various different redshifts that we're seeing. We're studying galaxy evolution by understanding how different galaxies move, galaxies at different redshifts are maybe connected. The local group is something like one slice here, but just run through time, okay? So the way we can understand the local group is by these reconstructions of the star formation history, which are limited essentially by the time resolution to which we can accurately date stars on these color magnitude diagrams. So you can think about the local group as something like infinitely thin slices, essentially, of something like the Hubble ultra-deep field. JWST era, of course, JWST has pretty much the same field of view as Hubble, so this is not going to be any different there, really. And so in my opinion, this gives support to the idea that the local group is a more typical region of the universe at early times, and certainly at redshift 7 in the reionization era, the RMS fluctuations of mass in squares of the size of the local group is significantly less than 1. Okay, so these are not nonlinear regions. They're firmly in the linear regime at that time. So I think studying reionization relics nearby is cosmologically relevant as well as just kind of interesting overall. Okay, so to do this, of course, we need to understand the star formation history at these oldest times. And again, we need to get to the oldest main sequence turnoff to do that. Shallow imaging basically could tell you, you get any result that you want about the star formation history of a local group galaxy from that. You could think that 50% of the stars were formed by the end of reionization, or 0 for this kind of thing. Just to give a little bit of a highlight, this is a slide Dan Weiss put together about what JWST will do for the local group. So here we have just an XY projection of galaxies that we know of nearby. Okay, and it's megaparsecs, or something like 16 megaparsecs on a side. If we want to go out in this very central region, sort of probing the local group, 1.2 megaparsec sphere around us today, well, pretty much any galaxy in 2 to 4 hours, you can reach the oldest main sequence turnoff. So this is per galaxy calculation. Okay, and again, that's probing something like a 7 megaparsec box at redshift 7. If we want to go out a little bit further, we can go to 2 to 3 megaparsecs today. That requires exposure times of something like 10 to 20 hours per galaxy. But now you're not just getting the local group, you're starting to get to the edge of these other groups. Okay, so M81, CEN-A, NGC 253. And if we go out to 4 to 5 megaparsecs, well, this is a significant investment of time, but you can actually start to really get galaxy formation over a whole range of environments if one really wants to. So this is just to give a sense of what you can actually do with JWST via resolved stars in the nearby universe. To compare with what you actually get in the high redshift universe, well, this is what the JWST might actually see of the local group in the early universe. It'll probably see the progenitor of the Milky Way and Andromeda, and not much else. Okay, and I'll come back to that in a minute. Maybe we'll get a Magellanic Cloud, something like that. With HST or JWST in the nearby universe, you can actually probe all of the kind of little dinky galaxies floating around and just get a tremendous amount of information. So to me, this is highly complementary to actually JWST's direct observation. I hope that Space Telescope calling to say that we're getting funded for all this. Excellent. Okay, so a little bit more about the high redshift context. We heard earlier today about the luminosity function, so I want to talk a little bit about this as well. So with the local group, we can actually ask things about, like, what do the progenitors of the local group dwarfs look like at high redshift? And potentially the reverse direction, what will high redshift galaxies evolve to be at the present day? So this is sort of the limit of the Hubble ultra-deep field now without lensing, something like minus 17 in UV luminosity. Steve mentioned this. Richard talked about it. At redshift 7, this is a luminosity function that I've plotted here that just is extrapolated with a faint end slope of minus 2 to very faint magnitudes. Again, this is sort of what you can do with Hubble. This is what the frontier fields can do with a magnification of 5 or 10, a factor of 5 or 10, not 5 or 10 magnitudes, obviously. And JWST in blank fields will sort of get to what frontier fields can do in a magnification of 10, okay? But we've heard a lot about galaxy-driven reionization potentially requiring much fainter sources. Now, this is a little bit uncertain, but it seems fairly clear that if it's all galaxy-driven reionization, we're not going to be seeing the full population of galaxies that are doing the reionization. So Eric asked earlier about some numbers. These are approximate numbers in terms of star formation rates. Minus 18 is something like a star formation rate of 1 solar mass per year. Minus 15.5 is 0.1. And if we want to go all the way down to minus 10, we're talking about something like 1,000th of a solar mass per year. Now what you can do with these star formation histories that we've actually calculated is put them through stellar population synthesis modeling and predict what local group galaxies actually looked like in the reionization era. Okay? So here's what the LMC would have looked like potentially in the reionization era. Would have had a star formation rate of around 0.1 solar mass per year. And so it would be at minus 16 or so. So again, the Hubble deep fields aren't probing galaxies like the LMC. So even the biggest dwarfs we have in the nearby universe aren't the galaxies that are being seen in the Hubble deep fields. Galaxies that are a factor of 100 or so less in stellar mass, these are sort of bright Milky Way dwarf satellites, Fornax, Sculptor, Leo A. These all would fall around minus 13 to minus 11 or so in the reionization era. And there are, of course, even fainter galaxies, so Draco, Leo T. These are down by another factor of 100, so present-day stellar mass of a few times 10 to the 5, and they'd fall below minus 10. Right? And these aren't even the faintest. Right? There are galaxies that go even fainter still. So I'd say that the luminosity function definitely should continue much further down. The question is, what does it look like? Does it look like this steep slope? Okay. And just to point out what can be done in the frontier fields, the Livermore et al. Detection at redshift 6 is of a galaxy at around minus 12.5, I think. And so that would lie here. So that's a tremendous leap, but we, of course, need statistics. And to me, this gives the complementarity between the local group studies of high redshift science and the actual direct observations, because there's nothing in the local group that's going to give you anything about this bright end. But the local group will really give you a lot of information about this faint end that's extremely difficult to get. One thing to point out is that if we're talking about star formation rates of, say, 10 to the minus 3 solar masses per year, well, that's nothing, right? But on the other hand, that'll form 10 to the 6 solar masses of stars, even if you just have a gigayear of star formation. 10 to the 6 solar masses is not a lot for people who do high redshift stuff. It's a lot for people who study the local group. It's really easy to see those galaxies. We think we know every 10 to the 6 solar mass galaxy within the Milky Way, and possibly even significantly further out. Okay? So this is significantly more stellar mass than even some of the classical dwarf spheroidals. So to me, archaeological studies in the local group with this stellar fossil record are probing descendants of systems that we're never going to be able to see directly, and that's really interesting. And another point there is that we know there are galaxies with these very low UV luminosities in the high redshift universe. If they had higher UV luminosities, they would have just formed a lot more stars than we can see around today. So that means that there are a couple of things here. I don't think we should expect a sharp cutoff in the galaxy luminosity function anywhere that's going to be observationally probable with any of these facilities, JWST, HST, whatever. We know there should be galaxies, and lots of them, that have UV luminosities or UV magnitudes that are minus 5 or even fainter in the reionization era. But just from counts in the local group, I think we can also say that the steep high redshift luminosity function can't continue all the way down. And the reason for that is that if you just keep populating galaxies into the dark matter halos that are available, okay, this is what I'm trying to show here, you get a luminosity function that would go something like this, okay? But you have a halo mass function that's much, much steeper, all right? And so we'd expect that you should be missing a factor of maybe 100 galaxies in the high redshift universe if you probe all the way down here. We know what the galaxies actually look like. This is where Fornax would sit. This is where Draco would sit. And there's something like 100 galaxies at this halo mass that are missing then. Now, if you instead postulate that you actually break this luminosity function to a slightly shallower slope, something like minus 1.2 at around minus 13, you do much better in populating the luminosity function with the dark matter halos we think are around in the local group. Okay? And the other thing that this would actually then predict is that all of the star formation for these galaxies is happening in halos above the atomic cooling limit. So that's around 10 to the 8 solar masses at redshift 7. In this kind of model, you'd be populating well below the atomic cooling limit just to get down not even to Draco. So here you probably can get 100 galaxies or so without going below the atomic cooling limit. I'll just skip over this and say that essentially with this steep slope, you're vastly over-predicting counts in the local group. With a broken luminosity function, you're matching the local group counts. You're still getting reionization. You're consistent with everything. So this is a prediction we can kind of make. And as JWST studies the local universe, LSST finds more dwarfs. This can kind of be tested directly. So to summarize, I think the local group is where we can best observe low-mass dark matter halos and the faintest galaxies. And the stellar fossil record, or galactic archaeology, one aspect of galactic archaeology, gives us a way to study systems that are too faint to ever be observed directly in the high redshift universe. So to me, this is a really good complement to actually trying to study cosmic dawn at cosmic dawn. I tried to argue the local group collapsed from a region that's securely in the linear regime at high redshift, and that makes its faint galaxy population representative of the galaxy population at large. I've argued there shouldn't be any sharp cutoff in the galaxy luminosity function at high redshift, at least not down to very faint magnitudes. But data in the local group are consistent with at least a break in the luminosity function at around -13 in order not to overproduce the Milky Way satellites. Thanks.
Eric?
So, my recollection from the models of how stellar halos grow in a cosmological context is that of order 90% of the satellites that formed in the local group are now incorporated in the stellar halo and are no longer recognizable. How do you account, I'm sure you're accounting for this, but how are you kind of keeping the books clean when you're doing this exercise? Because if 90% of the galaxies that were around at redshift 7 go missing and get shredded, then you're not counting them with Fornax and Draco, et cetera, then you're counting them differently.
Right, so there have been two different kind of parts here, and so that accounting has to be done differently in a couple of them. So if you're just doing constraints saying, look at the observable things today, what does that tell us about star formation at high redshift? We're only looking at the surviving ones today, and so there we're doing a one-to-one accounting. When we actually want to understand, okay, where was everything previously, it's true we don't actually know where everything ends up. So some of these things may end up destroyed. Some of them may end up not destroyed in the high redshift universe. But since we're studying them in the local group, we're really asking the reverse question, which is taking things we see today and running the clock backwards and saying what was there. So this is actually giving us kind of a lower limit on the things that would have been around in the earliest times. So if we could actually take it and run the clock forward, we'd certainly have to worry about that. And we're trying to do things theoretically in that way. And then we do have to worry about this a lot. And I think the stellar halo is going to be a really interesting test ground for that.
Brent?
It's odd to defend the UDF based on cosmic variance. But, you know, the volume is 50 times larger than what is probed by the local volumes. So that's, you know, just out there. The question I wanted to ask was about the hierarchical buildup of mass in these low mass halos. So when you do this transformation from the from the present time to early times, what do you assume about what fraction of the star formation occurs in non-main progenitor halos in those galaxies?
Right. So in the reconstructed star formation histories, we have no understanding of which one is in the major versus which one is merged. All we know is that the piece that we see today formed its stars by this fraction, unknown over how that's split over progenitors. And so I think that's certainly an interesting thing we can try to ask. Would we see signatures of mergers in this? Yeah, exactly. I think we'd certainly see signatures of, say, triggered star formation if that was a significant fraction of the star formation history. Yeah, I think chemistry is definitely another way to look at this. From the simulation point of view, and just from the dark matter simulation point of view as well as a hydro point of view, you don't get that many mergers on the scale of dwarfs at late time, so very few of these will undergo lots of merging. And so we expect that something like 80% of the stars formed in the main progenitor, but there is variety around that, presumably, and we'd have to understand that better.
You want to, well, keep the mic on, I guess you need to respond. Last question.
Great talk, Mike. I don't
Thank
know
you.
if this I don't know if this question makes any sense, but you could, in principle, derive. For example, a redshift of 3 or 4, how many UV photons those local group dwarfs should be emitting, and maybe you can compare to the measured UV luminosity function at redshift 3 or 4. Maybe you can get a very good handle on extinction, for example, because the intrinsic production, in principle.
Yeah, that's right. I think there's definitely a lot to be done there. And Dan Weiss has done some studies on the UV luminosity functions themselves, not the actual stellar mass functions, or just putting things at the UV luminosity as they were, but reconstructing the full UV luminosity function. I think there's definitely more to be done there. Sort of limited by hours in the day right now, but I agree that's a very interesting avenue to take.
Great. Let's thank Michael again.